laboratories and stepping into our lives. Will they help us? Or will they replace us? Even the people who create them can't agree. But whether humanity likes it or not, the robots are rising. And our world will never be the same.
No, not that. You, I suppose you're programmed for etiquette and protocol.
Protocol? Why, it's my primary function, sir. I am well versed in all the customs. That is why I have been programmed.
What I really need is a droid who understands the binary language of moisture evaporation.
These are the robots of our dreams. Intelligent machines that live to serve.
Can you speak Bocce?
Of course I can, sir. It's like a second language to me.
And these are the robots of our nightmares. Mechanical predators hell-bent on replacing their creators.
I think the idea of people fearing robots is almost a myth. I'm not so sure that people imagine that robots will bring direct harm to them, but it may be the cultural changes and the changes in the way we do things may have impact or consequence in people's lives or workplace or the way that we do things. And it's that notion of change that seems to be the great concern.
A robot is a machine that performs useful actions and is capable of making decisions about its behavior. In other words, robots are the love children of computers and power tools. They come in all shapes and sizes, each specific to its function. As we shall see, some of them even resemble the artificial humans of the movies. But until very recently, robots in the real world looked more like toasters than the Terminator. Since they first came on the scene in the 1960s, real-world robots have slowly worked their way into industry, taking over more and more dirty, dull, and dangerous jobs with each passing year. In assembly line businesses, such as building cars, the ability of robots to perform complicated tasks over and over is a perfect fit. But getting robots off of their pedestals and into the world at large has proven far more difficult than science fiction films would have you believe. This is beginning to change. The revolution in computing power, combined with unorthodox new approaches to building robot brains, has resulted in a revolution in robotics technology. In the near future, the worlds of fantasy and reality may converge. When that happens, will we be ready for it?
RoboCop. You better back up, pal!
Your move, creep.
This is the fantasy vision of police robots. And this is the reality. In Washington, D.C., the U.S. Capitol Police raced to the site of a suspected bomb. The Capitol Police are charged with protecting Congress, much as the Secret Service defends the president. These officers have to be more cautious than ever before. Terrorists have begun to plant 2 bombs at their target sites. The primary bomb explodes first, followed by a secondary device that's left to kill the policemen who come to investigate.
Things have changed a lot. We talked about secondary devices for years, and now we're starting to see them on actual incidents in the U.S. They've been common in Europe for some time. And the degree of sophistication has increased to the point where there are literally proximity devices, which used to be limited to military explosives that explode when you approach them. They just sense a change in the magnetic field and off they go.
What's it look like? Well, it looks like a box. Wooden about this big.
When an experienced officer identifies a suspicious package as a bomb, the police take no chances. They send in the Andros 5. The Andros 5 robot has become the tool of choice for bomb squads in high-risk areas around the world. The robot's popularity is a sad reflection of the increasing danger of law enforcement. The machine is teleoperated, which means that its actions are controlled from a safe distance by the bomb squad. Guiding its multiple claws and cameras takes practice, but most officers feel it's worth the effort.
Actually, I'd like to send the robot in every time. It makes my job a whole lot safer. And I think our job is relatively safe with our training and equipment, but there's that word relative, and there's zero risk in sending the robot in. And if the robot bites the dust, well, I'm still here to requisition another one, and I've got all of my extremities to do it with. It's just a mechanical loss.
Now comes the most critical part of the operation. The robot must drop the bomb into a custom-made sphere that will absorb the shock of an explosion. Somewhere in New Mexico, a fighter-bomber has crashed. The military needs to get a nuclear weapon out of the burning wreckage. They send in a robotic Humvee. These are the jobs that robots are beginning to take on. Jobs that literally nobody wants to do. Again, it's what roboticists call the 3 Ds: dirty, dull, and dangerous work. Like the Andros 5, this robot is teleoperated. The Humvee can drive largely by itself, but its arms are completely controlled by a human operator. This is the key question of robotics. How smart does the machine need to be? The answer most roboticists give is simple. It must be smart enough to get the job done. In some cases, you wouldn't want to trust a machine to do everything. But the strain of controlling every tiny movement from afar is often too much for teleoperators, especially if there's a time delay between human action and machine response. The newest robots use the faster, cheaper computers available today to let robots think for themselves, at least up to a point. There are 3 basic ways to make robots work. An intelligent teleoperated system has some computerized control at the robot end, but a human makes virtually all of the decisions. With supervisory control, the human makes key decisions about what the robot should do, and the robot has enough intelligence to perform its tasks without constant guidance. An autonomous robot is virtually free of human control. This might not always be a good thing.
Tobor, the most amazing, the most fantastic creation of man's mind.
Oh, he looks alive.
Tobor, bringing you chills you've never known before.
People's perceptions of robots as compared to what they really are is one of the biggest problems that we have to face as roboticists, because Hollywood keeps on perceiving these robots and projecting them as competent, capable machines that will take over your world when you're not looking. When in actual fact, it's very hard for a robot even to get its steely butt off the ground, let alone wander around a room and actually do something like, say, vacuum it. The real future for these things, we feel, is when we can finally break that barrier, when you can finally take machines away from the little boxes that we have to put them in, like factories or even computers, and give them the power to be able to interact in the real world.
In the mid-1990s, the two Dante robots became famous for their adventures out in the most remote parts of the real world. These 8-legged tethered machines climbed into active volcanoes in Alaska and Antarctica. The first Dante broke down almost immediately when its fiber optic communication line froze and snapped. The second robot fared much better. For days, it crawled around a volcanic crater, sampling toxic gases.
Landing, I think we're ready to stand up and try stroking and turning.
Dante was controlled using satellite links to the continental United States. The machine received basic instructions, then slowly plotted out its descent into the crater. The mission was overseen by NASA robotics chief Dave Lavery.
With the Dante projects, basically I was responsible as the NASA telerobotics program manager for being the NASA representative for both field parties, Dante 1 and Dante 2.
Get a second heading, give us your tether payout.
The real significance of both projects, one, it was a demonstration that the technology associated with the robotics was ready to make the leap out of a laboratory environment into a real, harsh, realistic setting. And you can't get anything that's more harsh than a polar volcano as far as we've been able to find on this planet. And yet the robotics technology has shown that there's a capability there for safely delivering a science package into a volcano interior and then bring the data back out without endangering any human lives.
Dante was a product of Carnegie Mellon University, the headquarters of one of the major figures in robotics today. Red Whitaker is a former Marine who has made it his life's work to build robots that can function in harsh environments. He is the de facto leader of the top-down approach to robotics, which mimics the way humans, the animals at the top of the food chain, interact with their world. Whitaker's robots are programmed with an advanced knowledge of their surroundings. Every action they take is carefully considered and weighed against an overall plan formed by their computer brains. They are also notoriously big.
I've already been thinking ahead to next design on this thing, and something more monolithic, maybe get the...
My first 50 robots probably have the rap of being the mega robots, the big guys that Red builds big machines. And whether it's a mouse or a moose, the thing that's important is that it's appropriate to its purpose. I was a little restless in my world, looking for something different and more, and computing was already a little far along. I sought something that would be pioneering, true invention and creation, and also good for decades, and something that would impact, make a difference in my lifetime. I chose robots. The real galvanizing event was taking on development of the machines to clean up the 3 Mile Island nuclear accident, and that experience then set the course for a career.
Whitaker's company, Red Zone, has made a full-time business out of building robots that go where humans fear to tread. This is Rosie, a robot that decontaminates and dismantles aging nuclear facilities. In a few days, Rosie will be sent away to tear apart a reactor near Chicago. Rosie costs $750,000. Once she goes into service, she's expected to function without failure. No one will be able to fix her when she's radioactive. Houdini is a Red Zone robot that works at the Oak Ridge nuclear weapons plant. After lowering itself into a hazardous waste tank, Houdini uses a dozen different tools to scoop up and store away sludge so lethal it could kill most of the life on Earth. Whitaker's robots are very functional, but, he will admit, they aren't very glamorous.
In the early going, things were simple. Form followed function, and the only challenge was to get a robot to navigate or clean up a nuke setting or to perform an industrial task. Now people actually expect robots to look like robots and to speak like robots. The Ambler robot behind us did in fact think about where it would move, that it would be moving its left foot forward and then crowding the next obstacle to leave room for the right foot to get up and on, and actually to express what it was doing and what it was about. And people actually were enchanted by that. I think that next generation robots have to master that kind of speech and interaction a lot more than their personal status or the weather report, but to really interact in the way that we are right now.
Whitaker's early robots were among the first that could function outside of a laboratory without constantly breaking down. But apart from Whitaker, no one had much luck making robots that could reliably find their way through unpredictable environments. And no one at all could make their machines move quickly. Then along came Rodney Brooks, the inventor of the bottom-up approach to robotics, which mimics the behavior of creatures at the bottom of the food chain.
Back in the early 80s, robots were very, very slow. They were connected to mainframe computers. They would compute for minutes at a time before the robot could move even a meter. And if anything changed in the world in the meantime, they were completely lost what was going on. And I looked around at insects, and insects, could fly around at a meter or so per second. They could avoid getting eaten by a bird. They could chase prey that they were after. They could go through mating behaviors. So it seemed to me that maybe we were organizing the computation the wrong way in the way we were approaching robots. And that maybe by trying to organize the computation a little more like it's organized in insects, we would get much better performance.
Brooks' insect robots aren't intelligent the way we think of humans or even computers as being. Instead, they operate on patterns of behavior. When you turn them on, they're brainless. But with each step they take, they learn how to adapt to their environments. Rather than having a standard central controller, these robots have separate layers of behaviors that are independent but which communicate. No advanced behavior can start unless the simpler ones are up and running.
When I first started talking about these ideas, the only good thing going for me was I had videotapes of robots really doing things that other robots weren't doing. Otherwise it would have been dismissed as a total flake, and probably would have been a total flake. But because I had some performance, people looked at it and thought, well, maybe there's something there, but there was still a lot of arguments with me and a lot of resistance. Now, over time, people who actually build robots have generally come to accept this approach at the low-level aspects of controlling a robot, and it's become the standard way to operate.
Unlike Whitaker, Brooks is not an engineer. His specialty is building brains. The robot's bodies are made by his colleagues and students at MIT. But like Whitaker, Brooks is ambitious and not opposed to making money. Brooks is now chairman of IS Robotics, the bottom-up version of Red Zone.
How are the new tracks going?
I guess
Virtually everyone on staff is an MIT alumnus. They all share the dream of putting a robot in every living room.
This week or next week we'll get that set.
But right now, many of their robots are paid for by the people who brought you duct tape and the internet, the United States military. The IS concept is to build swarms of small, inexpensive robots that can cover terrain too dangerous for troops to enter. This minesweeper is designed to be carried by soldiers into combat zones. The controls are strictly supervisory. The machine finds its way through the world in the same brainless fashion as Brooks' insect robots. Ariel is an underwater minesweeper built for the Navy. The idea is that before soldiers hit the beach, dozens of these robots will march in and sacrifice themselves on enemy booby traps. body was based on a crab. If currents throw it about, it can operate upside down. IS also sells versions of the Genghis robot to labs around the world. The original Genghis launched the insect robot revolution. It was built by Colin Angle, a one-time grad student of Brooks who is now head of IS. Angle and Brooks believe the entertainment market could provide the monetary push that commercial robotics needs. Much as computer games helped finance the microprocessor boom, a must-have robot toy could fuel the next high-tech revolution. This robot baby doll might be the start of something big.
So the doll is capable of sensing lots of different interactions. Before it gets too upset and really all it wants to do is nap and eat, we can demonstrate some of these things. Like he likes to play patty cake. He can. He's just singing a song that he sings when he plays patty cake, and he likes. You can see he's kind of like that. He also likes to bounce. But of course, bouncing the baby like I'm doing also is very tiring for the baby. So as long as I keep doing it, he'll be in a good mood. But if I stop like I did, he's going to very, very rapidly get upset
and crash.
So we should give him his bottle rod. Why don't you demonstrate that?
Yes, he's not being real happy right now. Oh, that's better. That's much better.
Well, we've instrumented the doll with a number of different sensors. Like inside the body, there's a ball in a cage, and we can sense where that ball is and where it's moving, and we can detect rhythms. So we use that to determine rocking and orientation, and if Rod was to hold it upside down, it really doesn't like that, and it's going to start. It'll fairly quickly start to cry. And so that puts in a really bad mood.
We really did upset it by holding it upside down, because it's got these various drives that need to be satiated, and certain emotions that get excited by both good things and bad things.
Give it a hug.
And the hugging sort of lets it get a little happier.
It's a very reassuring and comforting sort of thing. So you can see we've improved his mood measurably by giving it a little TLC here.
In robotics, a lot of us feel like we've been cheated by Hollywood, in that Hollywood has shown robots doing things that we don't have any possible capability of doing with our robots right now. So people are disappointed when they see our real robots. On the other hand, I'm more optimistic now than I was 5 years ago that we're going to eventually catch up with Hollywood, and maybe before too long, maybe even in my lifetime, be doing a few things that Hollywood hasn't thought of just yet.
Like what?
Oh, I haven't thought of them either. Leave it as a mystery.
The animal kingdom is filled with millions of different designs for creatures far more capable than today's robots. But as Rodney Brooks has shown, building machines based on lower forms of life is a promising path on the road to the ultimate goal, creating an artificial human. The ongoing miniaturization of computer processors and parts has resulted in the first wave of machine copies of organic life, what science fiction films call replicants. And nobody builds replicants as well as the men and women at the Massachusetts Institute of Technology. MIT's Leg Lab is constructing a motley assortment of replicants, ranging from robotic flamingos to creatures that defy description.
Robop's the official name.
Rob doesn't like that.
It doesn't really have a name.
In our laboratory, how to name the thing. Sort of like naming a child, you know.
Okay, here we go.
The secret to getting these machines to run, walk, and hop is a combination of nuts and bolts engineering and savvy software writing. This one-legged robot has no onboard computer. It's kept upright by pure physics. But when the robots have multiple legs, they're propped up by something called virtual model control. The machines are tricked into keeping their balance by a simulated spinal cord built into their computer brains. The virtual spinal cord lets this robot, called Spring Turkey, walk on 2 legs. Until recently, this was considered impossible. But the Leg Lab tackles the impossible every day. For instance, Peter Dilworth is trying to bring dinosaurs back to life. Working from the skeleton of a troodon, he has painstakingly assembled a 2-legged robot that he hopes will walk and run like the monsters of the Mesozoic. Ultimately, he would like to build a zoo filled with dinosaur replicants. Like many young roboticists, Dilworth's work has been inspired by science fiction.
One of the things that really got me interested was this little guy. This is the robotic soldier from Star Wars. The whole idea of seeing these robots in the movies convinced me that it must be possible to actually make them. They look so real, and I felt that, you know, why can't I make that? Why can't I bring that into existence? The trick of making a robot walk is being able to control forces on the legs, at least as far as walking bipedally, walking with 2 legs is concerned. I mean, there are robots with 6 legs, hexapod robots that can walk and crawl, but they're statically stable. But in the case of this robot, a biped robot, the balance of the robot is much more complex. And in order to maintain balance, you need to be able to push against the ground very carefully, you know, with just the right amount of pressure. And you need to be able to sense how much pressure you're feeling on your leg, because that information, the sense of how much force you're using, is an important part of figuring out what your balance is.
Replication doesn't just mean imitating a creature's physical movements. It can also mean emulating the way they behave. Creatures like ants, which are driven entirely by instinct, manage to accomplish great feats by pooling their limited intelligence. Could the same thing happen with machines of limited intelligence? James McClurkin has studied the way that insect colonies function by building robot ants that communicate using infrared devices. The robots signal each other if they find food, and they learn to cooperate to solve simple problems.
When you make robots small, you have a lot of advantages due to their size. You can put them places where you can't get larger robots. You could have them foraging around through nuclear power plants, going through pipes, looking for cracks. You could even put them in the human body, use them for surgery. We were being funded 2 years ago to work on surgical robots about this big. They would go through your large intestine and perform surgery. So small robots are good. The only problem is that when you have small robots, they tend to be small. So one of them can't get very much done. You like to have a community of them working together to run around and collect dirt from under your refrigerator or spy in a building. In the building, you'd want, at the very least, all of them to avoid each other, so you wouldn't all end up in the same room.
But some of the most promising work in replication is focused on the most diverse forms of life on Earth, the creatures of the sea. Mankind has long marveled at the grace and power of fish, which can propel themselves through ocean waters at great speed with minimal expenditure of energy. Wouldn't it be nice if we could take all of our sophisticated sensors and pack them into something small, fast, and capable of swimming the ocean? Something, for instance, like an artificial fish. This is MIT's Department of Ocean Engineering, the home of Robo-Tuna. The tuna, known as Charlie, is used to study how fish propel themselves through water at great speed. Modeled after the bluefin tuna, the fastest fish in the sea, Robo-Tuna looks and swims just like its real-life counterpart. It also squirts out a trail of phosphorescent dye that lets scientists analyze its underwater contortions. Ships and submarines of the future will incorporate the swimming lessons that Charlie is teaching. Robo-Tuna was such a success that it spawned a free-floating follow-up, Robo-Pike. Robo-Pike has a fiberglass rib cage that is wrapped in foam and lycra. Its movements are powered by 3 motors that drive an elaborate system of internal cables and pulleys. These duplicate a real pike's muscles and tendons. Affectionately called Wanda by its chief designer, John Kumpf, Robo-Pike is a great leap forward in the quest to build a genuine replicant.
I was an undergrad walking through the halls at MIT, and I saw a sign on the wall that said, "Come work on a robot fish." And so I don't know, I knew that project was for me. I never thought it would, I never guessed, but I was already into robots, and I already worked a little bit in the field, and it looked like a much more interesting project than most of the stuff out there. Most of the robots out there are kind of boring, like welding robots, or, they're just not, they didn't quite have the draw that this does. Pipe is going to be used to help us learn about swimming, and eventually we're going to do something like throw it into the ocean and ask it to go follow fish around and tell us what they do. And how come we can't get our craft to go through the water with as little energy as it takes for a fish to do it? I mean, what can they do that we can't, And so part of the mission of the bike is to figure that out, is to tell us, we can output sensors, and we can put computers on board and collect data, and we can find out exactly how this body and this undulating, this articulated mechanism, which is just like a fish, interacts with the water. So, nature already knows the solution. We have to go find out.
On a warm summer evening, John takes Robo-Pike for its first trial swim in Boston's Charles River.
When you start to approach a problem like this, you just develop a new respect for what goes into a living creature and how amazingly they're put together, and how they're filled with creativity and of a sort that makes you wonder if there really is a God.
It's early in the morning off the coast of Northern California, but the good ship Point Lobos has been underway for some time. Its mission is to bring a deep-sea diving robot called the Ventana to the site of an ocean research experiment. The Ventana is an ROV, remotely operated vehicle. It is equipped with 7 cameras, 4 onboard lasers for targeting, 2 robot arms, and an assortment of interchangeable claws and power tools. It's one of the hundreds of ocean-going robots in use around the world. ROVs are usually pressed into service by oil companies looking for offshore petroleum. But the Ventana is special. It belongs to the Monterey Bay Aquarium Research Institute, a nonprofit group funded with a hefty grant from the late David Packard of the computer giant Hewlett-Packard. The group, known as MBARI, conducts pure oceanographic research. They're trying to learn more about life in the darkest, most mysterious parts of the ocean. The Ventana regularly dives to depths of 5,000 feet, where the pressure is so great it could implode a human being. The pressure problem is compounded by the fact that the robot is an electrical device operating in deep water, so a leak would be catastrophic. Normally, the Ventana goes out on picture-taking missions of ocean life. Today, however, it's installing a scientific instrument in a canyon wall at the bottom of Monterey Bay.
Well, see what the lasers are right now? That's our seismometer site, that hole right
The
there.
mission is flown by a crew sitting in the belly of the Point Lobos.
Can you hold it here?
Yeah, go ahead. Just go ahead and zoom. I want to see how close we are to the wall. Yeah, there you go. That's good.
That's not a bad area.
Medium oil right away.
Well, right now, the ROV is balancing on a rock. So we have 5,000 pounds of vehicle trying to hold station.
You can do that?
Standing up on, just touching in one place on a rock that's sticking out on the left-hand side here. And while we're balancing on the rock, another pilot is controlling the manipulator.
Yeah, see, I can't swing anymore.
And trying to.
So what do you need me to do?
Fly
Fly up
that
in there?
Cylindrical housing that would hold a seismometer into the
Lateral
hole.
to starboard?
Yeah, I need.
He's got it.
Yeah, it's going.
MBARI does not operate any manned submersibles. They believe that robots are the future of deep-sea exploration. Humans will remain safely above water or even on land, while their robot proxies plumb the depths of the abyss. The same approach is being used to help mankind explore another inhospitable region, the black void of space. Santa Monica, California is a far cry from the vacuum of space, or even the surface of the moon or Mars. Yet it's here that roboticists have gathered for a planetary rover roundup. Near the fogged-in beach, some of the best engineering minds in the world present a gaggle of wheeled, tracked, and legged devices that they hope will one day cross the sands of other worlds. They look slow and somewhat clumsy, but the fact that they move at all is a technological triumph. Rovers have to meet a set of requirements even more demanding than undersea robots. They must survive being shot into space, land on other moons and planets, and then operate in an alien environment for extended periods of time. If they break down, they're a long way from help.
I think this will conclude my demonstration. Thank you.
For this and many other reasons, most rovers move very slowly. A rover whizzing across terrain in low gravity could bounce on a rock and fly over the side of a cliff. This is good engineering, but it doesn't make for much of a spectacle. Still, these machines are the best hope the human race has in the next few decades to expand its knowledge about the origins of the universe. Manned space missions are now considered too dangerous and expensive to mount. Robotic astronauts will have to do our exploring for us.
Fundamentally, these rovers that you've seen today, some of them are designed for the moon, but largely we're looking at rovers that are designed to go to Mars. The pan and tilt mechanism.
15 years ago, we were really worried about simple little controls. How could we get it to do this little task or that little task? And today we actually handle most of those. You know, there's a whole realm of things that have to do with obstacle avoidance, which we still worry about, but is pretty well in hand. We pretty well understand how to do it. Now we have environments that are just wonderful for controlling a robot to get and do a task. And partially it's driven by advances in software and especially the advances in computing technology. Being smaller, cheaper, more powerful, lighter, it's just massively influenced what we're doing.
The vehicle that you see out here now.
Robotic explorers have actually flown in space for decades, bringing a set of eyes and ears to places human beings could never dream of visiting. The robotic space pioneers included America's Mariner, Viking, and Voyager, and Russia's Venera and Lunokhod. These celestial emissaries sent back the first close-up pictures of other worlds. They forever changed the way we see the universe. But the early probes had little onboard intelligence. At the time, computers were bulky and slow. Almost all spacecraft actions were controlled from the Earth. The next generation of space robots are smaller and smarter. They have enough brains on board to take orders without second-to-second supervision. Mars Pathfinder was the first of a series of missions that NASA is sending to Mars roughly every 2 years. Pathfinder carried the Mars Sojourner, the first rover sent into space. Sojourner landed on Mars July 4th, 1997, thus becoming humanity's first semi-intelligent emissary to another world. At NASA's Jet Propulsion Laboratory, Rocky 7 is making its way across a rock-for-rock recreation of a Mars landing site. This rover is a great technological leap over Sojourner. Packed full of sensors and downsized computing power, Rocky is built to do much of its work without constant human guidance. In this case, a NASA controller sends Rocky a message saying, "Take a look at these 5 rocks and get a soil sample." Rocky works out for itself how to get to the rocks and what to do when it arrives. At the end of each mission, it will download its data to Earth, then wait for its next assignment. Eventually, fleets of small, inexpensive rovers could roam Mars and the Moon, paving the way for human pilgrims.
Robots have a number of different roles for space exploration. Probably the one that's most significant is to be a precursor for eventual human presence, especially on planetary surfaces. This is the idea where you want to send a robot, for example, to the surface of Mars to do a survey to find out what the chemical composition of the soil of the planet may be, to see if there's a way we can process that soil to get life-sustaining chemicals for the humans to utilize when they get there eventually. Then later on, they can actually be doing surveys for potential human landing sites or even preparation of a human habitat. So basically, a human flight that may come 10 or 15 or even 20 years later will have their house already built, sitting on the surface of Mars, waiting for them to just open the front door and move in and live.
This is the Space Systems Laboratory in College Park, Maryland. The SSL is building the Ranger space robot for NASA under conditions that reflect the realities of government budget cuts. Ranger is being largely designed and flown by a small band of enthusiastic scientists and grad students at the University of Maryland. Its parts were bought at hardware stores or handmade by the students themselves. Today, the team is placing Ranger into a water tank for a practice run of a mission it will soon fly in outer space. Serving as a kind of remotely operated auto mechanic, Ranger will float outside the International Space Station, performing tasks such as unscrewing panels and replacing parts. It's designed to reduce the number of hours astronauts have to spend on dangerous spacewalks. After NASA announced Ranger, Japan's National Space Development Agency declared that it had designed a similar robot that would be launched first. ETS-7 is being built by 3 of the biggest companies in the country. Japan wants to beat the U.S. to space with a telerobot for a simple reason: money is at stake. Robotics is a major growth industry, and the Japanese want to hold on to and expand upon their market. Their view is so long-term that corporations are working on the details of using robots to build settlements on the moon within the next 30 years. Rovers are also part of Japan's effort to restake humanity's claim on the moon. Later versions of this unique 3-wheel design have a good chance of roaming across the lunar soil, searching for valuable mineral deposits. The U.S. and Japan are in a semi-friendly technological Cold War. Like the U.S.-Soviet race of the 1960s, space is the initial place that this high-profile technology will be put on display. But no matter what nation owns the hardware, the result will benefit us all. The massive streams of data flowing back to Earth from our robots will let us see the universe in a unique, new way. Through the eyes of our spacefaring explorers, we'll know what it's like to float amongst the stars. You're looking at the world of tomorrow, as envisioned by survival research laboratories. SRL is a San Francisco-based performance art group. Their malevolent machines spurt napalm and battle to the death before audiences across the world. The group takes Army surplus ordnance and retools it to create these Roman circuses of destruction. It's a black-humored parody of military megadeth technology. But it is also a bleak vision of an apocalyptic future in which hunter-killer machines run wild. In the wake of the high-tech carnage of the Gulf War, it's not difficult to imagine that this cybernetic slaughterhouse could soon be duplicated in real life. But at the moment, battlefields ruled by autonomous robotic predators lie in the distant future. This is not to say that the wars to come will look anything like the wars of the past. The killing zones of the future are changing because the line between fighting men and fighting machines grows thinner every day. For all practical purposes, these soldiers are cyborgs. They are fully wired into the electronics attached to their bodies and built into their guns. They always know where they are and where their enemies are. Information is now a lethal weapon. Robots will have a place in this plugged-in battlefield, but they won't be pulling the trigger.
The idea of autonomous or even semi-autonomous killing robots is extremely difficult to imagine for a variety of reasons. It's difficult to imagine even very advanced future robots being able to develop the sort of flexibility and cunning that a human being would be able to exhibit, the ability to address and deal with novel situations and unforeseen circumstances. Robots, machines are capable of seeing things in terms of black and white, ones and zeros, whereas a human being is capable of seeing things in shades of gray, and that's really what's required for that sort of mission.
Military tradition is another barrier to putting killer robots on the battlefield. Since the dawn of civilization, great armies have been built around the skill and spirit of their fighting men. The idea of handing over the waging of war to machines does not sit well with professional soldiers. For this reason, most military robots today are unarmed spies. At Sandia National Laboratories, engineers have built a fleet of tele-operated robots that navigate hostile terrain and ferret their way deep behind enemy lines. Most of these machines are intended for use as scouts, ground equivalents of spy satellites or reconnaissance planes. Miniature rovers have their place here too. Their small size gives them access to areas that human spies find hard to penetrate. The same robotic control systems now being put into cars and trucks are finding their way into tanks. Supposedly, they will be used as decoys, though it's not hard to imagine a fully armed, tele-operated tank rolling across a battlefield. The army, of course, isn't talking. Sandia's Fire Ant is a tele-operated robot with fangs. The vehicle drives out to a lonely spot, then waits for its prey. Unmanned flying robots are increasingly common in today's Air Force. Drone planes have flown since the Second World War, but today they're flying at all altitudes, often for days on end. Here, too, their primary mission is collecting intelligence. They provide continuous real-time information about the battlefield. But the best-known flying robot is also the deadliest. Since their introduction in the 1950s, cruise missiles have proven themselves easily as lethal as the Terminator, and perhaps a bit smarter. They can fly at rooftop level for hundreds of miles. They make decisions about their course, changing direction as they encounter obstacles. And they are notoriously proficient at finding and fatally striking their targets.
The technology component of military operations has continued to grow over time and will continue to as our technological sophistication as a society and as a world increases. That does not suggest, however, that the future battlefield will be empty of human beings and wars fought by machines against other machines. The more likely scenario is human soldiers working alongside robots, sort of in tandem, and the military is only just now beginning to explore where the synergies might be found of using robotic systems with human soldiers.
Well, it looks like a box, wooden about this big.
When an experienced officer identifies a suspicious package as a bomb, the police take no chances. They send in the Andros 5. The Andros 5 robot has become the tool of choice for bomb squads in high-risk areas around the world. The robot's popularity is a sad reflection of the increasing danger of law enforcement. The machine is tele-operated, which means that its actions are controlled from a safe distance by the bomb squad. Guiding its multiple claws and cameras takes practice, but most officers feel it's worth the effort.
Actually, I'd like to send the robot in every time. It makes my job a whole lot safer. And I think our job is relatively safe with our training and equipment, but there's that word relative, and there's zero risk in sending the robot in. And if the robot bites the dust, well, I'm still here to requisition another one, and I've got all of my extremities to do it with. It's just a mechanical loss.
Now comes the most critical part of the operation. The robot must drop the bomb into a custom-made sphere that will absorb the shock of an explosion. Somewhere in New Mexico, a fighter-bomber has crashed. The military needs to get a nuclear weapon out of the burning wreckage. They send in a robotic Humvee. These are the jobs that robots are beginning to take on. Jobs that literally nobody wants to do. Again, it's what roboticists call the 3Ds: dirty, dull, and dangerous work. Like the Andros 5, This robot is teleoperated. The Humvee can drive largely by itself, but its arms are completely controlled by a human operator. This is the key question of robotics. How smart does the machine need to be? The answer most roboticists give is simple. It must be smart enough to get the job done. In some cases, you wouldn't want to trust a machine to do everything. But the strain of controlling every tiny movement from afar is often too much for teleoperators, especially if there's a time delay between human action and machine response. The newest robots use the faster, cheaper computers available today to let robots think for themselves, at least up to a point. There are three basic ways to make robots work. An intelligent, teleoperated system has some computerized control at the robot end, but a human makes virtually all of the decisions. With supervisory control, the human makes key decisions about what the robot should do, and the robot has enough intelligence to perform its tasks without constant guidance. An autonomous robot is virtually free of human control. This might not always be a good thing.
Tobor, the most amazing, the most fantastic creation of man's mind.
Oh, he looks alive.
Tobor, bringing you chills you've never known before.
People's perceptions of robots as compared to what they really are is one of the biggest problems.
It's like a second language to me.
And these are the robots of our nightmares, mechanical predators hell-bent on replacing their creators.
I think the idea of people fearing robots is almost a myth. I'm not so sure that people imagine that robots will bring direct harm to them, but it may be the cultural changes and the changes in the way we do things may have impact or consequence in people's lives or workplace or the way that we do things. And it's that notion of change that seems to be the great concern.
A robot is a machine that performs useful actions and is capable of making decisions about its behavior. In other words, robots are the love children of computers and power tools. They come in all shapes and sizes, each specific to its function. As we shall see, some of them even resemble the artificial humans of the movies. But until very recently, robots in the real world looked more like toasters than the Terminator. Since they first came on the scene in the 1960s, real-world robots have slowly worked their way into industry, taking over more and more dirty, dull, and dangerous jobs with each passing year. In assembly line businesses, such as building cars, the ability of robots to perform complicated tasks over and over is a perfect fit. But getting robots off of their pedestal of the laboratories and stepping into our lives. Will they help us? Or will they replace us? Even the people who create them can't agree. But whether humanity likes it or not, the robots are rising. And our our world will never be the same.
Yeah, I'll take that red one. No, not that one.
You, I suppose you're programmed for etiquette and protocol.
Protocol? Why, it's my primary function, sir. I am well versed in all the customs. That is why I have been programmed.
What I really need is a droid who understands the binary language of moisture evaporation.
These are the robots of our dreams. Intelligent machines that live to serve.
Can you speak Bocce?
Of course I can, sir.
And into the world at large has proven far more difficult than science fiction films would have you believe. This is beginning to change. The revolution in computing power, combined with unorthodox new approaches to building robot brains, has resulted in a revolution in robotics technology. In the near future, the worlds of fantasy and reality may converge. When that happens, will we be ready for it?
RoboCop.
You better back up, pal!
Your move, creep.
This is the fantasy vision of police robots. And this is the reality. In Washington, D.C., the U.S. Capitol Police raced to the site of a suspected bomb. The Capitol Police are charged with protecting Congress, much as the Secret Service defends the president. These officers have to be more cautious than ever before. Terrorists have begun to plant 2 bombs at their target sites. The primary bomb explodes first, followed by a secondary device that's left to kill the policemen who come to investigate.
Things have changed a lot. We talked about secondary devices for years, and now we're starting to see them on actual incidents in the U.S. They've been common in Europe for some time. And the degree of sophistication has increased to the point where there are literally proximity devices, which used to be limited to military explosives that explode when you approach them. They just sense a change in the magnetic field and off they go.